Hello, everyone. First, I should remark that my talk may be somewhat different in the sense that's a bit less technical or technical in a different way, because if you look on the AtomDB website, one thing that the students among you will find on there is a pretty large package that contains a lot of cleaned data, a number of scripts that are hopefully well commented, and a README file that leads you through an analysis or parts of an analysis that I have done in a paper. And what I want to do with the talk itself is to give you some of the scientific background that is needed to do this hands-on exercise, what I call absorption resolved spectroscopy, mainly with a focus on high-mass X-ray binaries, because that's what I work on. But this whole talk could be understood as a call for, before you do high-resolution spectroscopy, make sure that you understand the variability of your source, if your source is indeed variable. And I'll also be, if you want to try things that are online, whichever spectral analysis package you want, I'll be available on Slack to discuss with that. So what this kind of hands-on tutorial wants is the transition, kind of show how we're doing the transition from time-resolved to absorption-resolved spectroscopy. So how do we disentangle absorption in high-mass X-ray binaries, and why is this important for high-resolution spectroscopy? Because of course we can do that not just for high-resolution data. As said, this is a little bit more about how to prep your data for high-resolution spectroscopy, and I also discuss high-mass X-ray binaries, but this can be applicable for any other sources where you do expect or can expect variable absorption. Things warp disk in low-mass X-ray binaries, to think long-term monitoring of AGN that may have clumpy tori. And I'm going to present some of the results so you have the scientific background from Hirsch et al. 2019, Maria Hirsch was a PhD student with Johan Wilms at the Remise Observatory, who wrote a really nice paper about that. And from my own paper from 2017, and the hands-on are from 2017. So the point is, we've seen this amazing spectrum of the Perseus cluster by Hitomi. And the point is, if you have something like a cluster or like IGM, that's super interesting, but it does not change on timescales of single observations. On the other hand, you may have something like this example here. So what you have here is a simulation of a star, the blue dot in the middle, and around it a wind, a clumpy wind, a wind that has structure in it. And you can imagine that something like that will change on timescales of a single observation. If you now want to understand this wind plasma, you have to somehow disentangle all the individual absorption events caused by those density perturbations in the wind. So kind of like the scientific background for that is twofold in high-mass X-ray binaries. First of all, we have winds in massive stars that are intrinsically line-driven, high-mass loids, high terminal velocities, unstable to velocity perturbations. The point is, if you look at simulations of winds like this, you see structures that have density fluctuations up to a factor of 100 and above. Now you illuminate a medium like that by your neutron star, and you immediately can imagine that the ionization structure of this medium is going to be different, but also that the absorption through this medium is not going to be a simple absorption through a smooth medium. And the other point is, especially in high-mass X-ray binaries where accretion happens, where stellar winds, if you have like even if you have just like a nice smooth structure out there, and you put a neutron star or a black hole in there and send it around, rotating around the star, you're going to have formation of structures in the accretion region. So something that we call accretion, photoionization wakes, and focused wind. And again, imagine we're observing a source like this. We're observing emission that comes from the compact object, and we have all this complex structure coming through our line of sight. And we want to understand the structure, obviously. So what we want to understand is wind properties. We want to understand those dense structures, things like size, shape. For that, especially, for example, for ionization structure, but also for composition of the clumps, we do need high-resolution spectroscopy. We may want to understand wind acceleration zone by looking at line shifts, We want to understand how the material that falls onto a compact object responds to changes in the radiation of the compact object. Again, high resolution spectroscopy. And we also want to understand this large scale accretion structure. So we have the formation of those dense arcs. Those can also be understood with the help of high ionization spectroscopy. And kind of those ideas is actually, as said, transferable to any other system that has variable absorbers whose properties we do want to know. If you're interested in particular in high mass X-ray binaries, there's a very nice review by Silvia Martinez-Nunes as a background. As said, so imagine we have our star, our clumps that are going in there, and we have our compact object going around the star. We only show the clumps here in this visualization in the line of sight. And what we have is varying absorption as those clumps pass through our lines of sight. And sorry about that. So what you see here is from the paper of Maria Hirsch, our observations of Cyg X-1. In the upper panel, you see the light curves, and you see how those light curves dip on comparatively short time scale. We are going to look at that in detail in a second. The point is that your typical crossing times of such overdensities through your line of sight is a few tenths to a few 100 seconds. And with today's instrument, as amazing as Chandra and XMM are, we cannot actually make a high resolution spectrum in a few 10 seconds. Also, usually not in 300 seconds. This is something that will be possible with Athena, but we are not quite there yet. But at the same time, the fact that we have this absorption gives us a chance to actually probe this, this emission. So once again, this is the same plot as before. So in the upper plot, you see the light curve. In the lower one, you see something that people actually not so often look at, and this is just simply X-ray hardness. So this is a change in spectral shape. And the one thing that you clearly see that those are clearly correlated. So my source does not just become dimmer during these dips, my source actually changes its shape. And this can be easily understood if you think about, well, this is increasing absorption, so more of your soft X-rays get reabsorbed. And we are going to get in a second to what this means for high resolution. But first of all, how do we actually kind of like decide looking on observations like this? So what I would like to do is I would like to sum up all those parts of the observation that happen at the same absorption level. I can, of course, do a simple cut in hardness. Actually, this is what will be done in the exercise, but there are actually slightly more clever ways to do that. And for that, we need to think about what is actually the underlying model. And this is a partial cover, something that's used pretty often, both in X-ray binaries and in AGN. So we have that can be either spatial, temporal, or for example, through a scattering halo, so you have some emission that still arrives at where you are, and so it's not, you model it with a partial cover, even so it's not really partial cover. And what you see on this plot here is what happens, what spectral shape you're actually having with increasing absorption. And I also show 3 different energy bands that are going to become important in a second. What I'm doing here, namely, is I'm plotting on the y-axis band A, band 1 divided by band 2, and on the y-axis band 3 divided by band 2 divided by band 3. And what I get out there are those very, very typical tracks. Along one of these tracks, one of these orange tracks is for one given covering fraction, and for variable absorption as I walk around the tracks. And this will become important in a second. Namely, when we look at what the actual data looks like, they have exactly this shape. So what we are seeing is actually this partial cover, and all our observations from the slide before. So from here, now plotted in those color diagrams. And what we can do now is we can actually cut in color space, and we can sum up all the observations that belong to a given absorption, no matter when during a single observation this happened. We get the same continuum shape, different absorption, and then we can do high resolution spectroscopy that actually gonna tell us something about this, the absorber. So as an example here, what you're looking at here are just ratio spectra for 4 levels of absorption, from non-absorbed to highly absorbed, again from Maria Hirsch's paper. And what you clearly see is, that my line content changes, which means that the material that is doing the absorption changes. And if you pay special attention, for example, if you are looking at helium-like silicon absorption, it's there in all observations. But if you look at something like silicon-8, it's not present at all in the non-absorbed spectrum, and becomes stronger as the absorption becomes stronger. This is something you can see in general for different lines. So these are silicon and sulfur lines, and the upper 2 line hydrogen-like and helium-like, and you see that as the absorption increases along the y-axis, they become weaker, while the lower ionization lines actually become stronger with the time. So what we are actually seeing is material that is less ionized along our line of sight. By the way, same Doppler shift for all the lines. So it's actually really the same material. So
you're just joining. We're going to wait another minute to try to get everybody back on.
Okay, I think I was here. So the point that I was trying to make was that by doing this resolution, this absorption resolved approach, and by applying high resolution techniques then to the absorption resolved spectra, we could actually uncover the structure of the plasma, even though that required pretty much looking at the data before we actually do the high resolution analysis. So the idea that we have there as an interpretation of structured clumps with cold cores, and this is also from Maria Hirsch's paper. I should have added a label to this slide, I'm sorry. However, the data from Maria's paper are pretty involved and pretty, like, it's 3 different observations, 4 different absorption stages, each 2 different regions. So what I provided for the students to try out is a different observation. So what we are looking on here is a source called Vela X-1. It's again the same thing, the same idea of a high mass X-ray binary, a neutron star, a normal star, wind structure, and this thing absorbing. And we are looking at the source at orbital phase 0.25. This is where absorption is the least, because all this large-scale structure is not in our line of sight. And people previously kind of said, well, this is kind of like the boring observation, because if you actually do take the whole observation and take the spectrum of the observation as a whole, it is actually comparatively boring. However, what's interesting is, again, if you actually look at the light curves of the source, and the first exercise online is to go to GGCAD and actually just take a look at it, you will see that source does a few flares. But if you actually also look into the hardness of the source, so again, it changes under the spectral shape, you're going to see that there are actually periods of increased hardness that do correspond to low flux, but not only. For example, here's a low flux period that does not go hand in hand with increased absorption. So we have a source that flares, but at the same time, we have changing variable absorption, changing stuff in front of the source. And this is the things that we are actually interested in. So again, similar to Cyg X-1, what we are doing is we are doing absorption resolved spectra. So spectra at different levels of absorption. So pretty much one spectrum in the gray regions here, one spectrum in the white regions here. You can choose whether you want to play with Chow and do the analysis yourself, or whether you want to just like take the data as it provide. we can look at the spectra overall. We do see a difference in flux because this low absorption region also contained a few flares, but we actually can describe them with the same slope, with a power law. So the changes that we see up here are really mostly changes in absorption. And again, similar to the case of Cyg X-1, if we actually look into the details of the spectra, if you look at the more high resolution details, we see already by eye that things did change. Just look at this like whoopingly strong forbidden line in the low absorption spectrum. And one of the interesting things that we did find is that during those periods of enhanced absorption, that if we look at the total spectrum, just kind of like just go overwhelmed by all the photons that come in during the other time, so we can't see those details, we actually do see high ionization stage of silicon and low ionization stage of silicon, but not necessarily those in between. In comparison, down here, it's actually lab measurements from Natalie Hell at Lawrence Livermore Lab. Hi, Natalie, if you're listening. So we can see that high and low ionization and ions are present in cold and colder gas that we also can try and interpret as, for example, hot part of the wind was colder clumps and then shocks. So the exercise that is online does not look into actually trying to model those data with, for example, photoionization models, also because this data is a little bit complex. But this is something that people have been asking me and us about. And for that, I want to point out to a paper in preparation that should be submitted within the next week by Roberto Amato, a PhD student here in Tübingen and in Palermo, who actually models those data at the different orbital phases, both cloudy and specs. So with, again, these two different models, as has been pointed out at the beginning in the very first talk, it's a good idea to use two different models to try to actually understand your systematics in there. So what do you have online? It's like data for hands-on. It's supposed to give you a feeling for the absorption resolved analysis of Vela X-1, as I've done in Vela in Grinberg et al. 2017. Step one is like take a look at time average spectrum. I'm going to send you to TGCAD because TGCAD is amazing, but you also have spectra provided in there. Step one is to look into the light curves and to look into how to create the GTI. And the step two is to look at the absorption result spectra and also like one block, because we use the Bayesian blocks method to do some narrow feature detection. And step two kind of like also provides a few short example scripts on how to do that. I usually do my analysis in Isaac interactive spectrum interpretation system, but you are free to go ahead and try to recreate the same analysis in whatever is your favorite system. And with that, I thank you. I'm not sure how we are on time given the interruption.
So you're within your time. We lost a few minutes when Zoom went down, but thank you so much. We have one question from Chris. For Vela X-1, it has emission lines as well as absorption lines. So how can you separate those?
It really depends kind of like on which orbital phase you're looking at. In that case, where we're looking at right now, this is a problem. This is also the reason why we did not go in and look into the details of photoionization models, for example, because we know that this is a system that's where both processes happens at the same time. What can guide us is to understanding the system at other orbital phases where we, for example, know that the source is so absorbed that at low energies we only see emission, or we mainly see, for example, the photoionization component. So that really depends on the orbital phase that we are looking at. And another point where what may be helpful is Athena, with, especially in the Silicon region, a higher resolution that might actually help us disentangle the two components, so the emission and the absorption components, because they may have a slight shift to each other. So we kind of do think those, we do see those V-shaped lines, but I think somebody is gonna talk about weak features. And right now, we really do not dare to interpret them. We see them by eye, but they are not statistically significant. So Athena, maybe also Chrism.